This is going to be a video on inverses mod n. It's going to be more of a quick and dirty kind of cheat sheet on how to compute inverses mod n. You can do this through a much more thorough process where we develop the group theory behind the set z mod n z, and that is very valuable and worthwhile, but I'm just going to do kind of a quicker bit of an intro of how we actually compute these. When I am typing, things do get kind of clickety-clackety on the recording since I am not using an external mic. I'll try to minimize that, but we just want to get the idea down here. So in general, we're going to talk about inverses mod n. I figured I'll show the LaTeX here as well. P mod means it just gives us the notation mod n with the parentheses around it. The set of integers mod n. So one way to write it is this z symbol with the double bar, which stands for the integers with the subscript n, meaning the integers in particular, mod n. And this is the set of all remainders or all possible remainders if you divide by n. The inverse, and here I'm saying multiplicative, but I'll drop that word in general. The multiplicative inverse of an integer a in Zn is an integer b in Zn, such that a times b equals b times a, which is congruent to 1 mod n. This three-lined equal sign just means it's equal to 1 mod n. We say congruent to, meaning it's the remainder, because technically a times b could equal something larger, but then when we take it mod n, it would come down to 1. So we use a symbol, but you can really think of it mostly as an equal sign. So I'm going to just start with an example of z5. I'll say example. So if we have z5, this contains 0 through 4. And we're going to just look at what the different inverses are for each thing in z5. We'll start with the easy one. 1 times 1 equals 1. So that means that the inverse of 1 mod 5 is just 1. The inverse of 1 mod any number is just going to be 1. We can say, two ways to kind of refer to this, the inverse. So 1 times 1 is 1 mod anything. So we can say the inverse of 1 mod 5 is 1, or we can say 1 inverse equals or is congruent to 1 mod 5. So 1 is the easy one. And then if we look at 2, you can kind of run through the different possibilities and you're like, well, 2 times 0 is 0. That's not going to be 1. 2 times 2 is 4. That's still not 1. 2 times 3 is 6, which is congruent to 1 mod 5. So this means that we can say a number of different things. We can say the inverse of 2 mod 5 is 3. We can say the inverse of 3 mod 5 is 2, because they're inverses of each other. I'm just going to say 2 inverse is 3 mod 5. And I can also, of course, say 3 inverse is 2 mod 5. Next, let's look at 4. Now, 4's inverse is going to be 4 mod 5. I'll show you why, and then I'll explain why I know that right away. So we know 4 times 4 is 16, and 16 divided by 5, of course, we get a remainder of 1, so we have that 4 inverse is 4. So I didn't have to, think about this too much. I know 4 is a relatively small number, so you don't have to think a lot anyway, but because 4 is just 1 less than 5, I actually knew it would be its own inverse. And there is a reason for that. It's that in this case, 4 is equivalent to -1 mod 5, and -1 times -1 equals +1. And that's something as you get more comfortable with, numbers mod n, you can start to think about more. But just as a quick, general cheat or general rule, if we're doing mod n, then the inverse of n minus 1, the inverse of one number below n, is always just going to be itself. So now we have the inverses for 1, 2, 3, and 4. I left 0 alone because, well, 0 doesn't have an inverse mod 5. And if you think about it, it's just because if you multiply 0 by anything, the product is still 0. So you're never going to be able to multiply 0 by something to get 1. So it's just not possible for 0 to have an inverse. In this case, everything has an inverse except for 0. That's not in general true. It's true in this case because 5 is a prime number. So every number other than 0 will have an inverse. But if we're working with something that's not a prime, it does get more complicated. So if we're working with z7, z11, or, the integers mod any prime number, we can find an inverse for absolutely everything in the set other than 0. If we're working without a prime number, we have to be a little more careful. Or let's just consider Zn in general. So if we have Zn, just in general, we don't know if n is a prime, we don't know anything about it other than it's a positive integer, what can we figure out? Any number a in the set Zn has an inverse mod n if a and n are relatively prime, which means that the greatest common divisor of a and n is equal to 1, aka if a and n don't share any factors other than 1. Let's do 30. So let's look at Z30. We're going to say which elements have inverses in Z30. And to answer this question, we want to look through all of the numbers 0 through 29 and just figure out which ones of those have no factors in common with 30. 1 always has an inverse of 1, but then we think through this list and we say, well, 2 has a factor in common with 30. They both have a 2. 3 has a factor in common with 30. 4 has a factor in common with 30. They're both divisible by 2. 5 has a factor in common with 30. The next number on the list after 1 that has no factors in common with 30 is 7. We think 8, nope, common factors, 9, 10, 11. 11 is next. Obviously, so far these are prime numbers, but they don't have to be all prime numbers that are going to end up on this list. So we still have to think through the whole thing. 12 has some factors in common. 13 does not. 17 is the next one that doesn't. And then we keep going. 18, that has some factors in common. 19 does not. 23 does not. And 29 does not. So these are the numbers that are relatively prime to 30. I know in this case they all ended up being prime numbers. That's not always going to be the case. It's partly due to my construction where I chose 30 because it was 2 times 3 times 5, so I chose it to be the product of the 3 smallest primes so that it would have a lot of things that it has factors in common with. So these are the elements that have inverses in Z30. So let's revisit the fact that, we know that 1 inverse is 1. So we'll just put that down there. 1 inverse is 1. 29 inverse is 29. This is that rule I said earlier where, the number that's just below your n. And then we can work from here. And it is, it takes some work, mostly an exhaustive search. I usually kind of look through the list and see, is there anything popping out at me that's going to maybe make my life a little easier? Maybe 11. 11 times 11 is 121. And 121 is 4 times 30 plus 1. Like 30 goes in 4 times and we have a remainder of 1. So 11 is also its own inverse. You don't have to do it this way where you look for things that are self-invertible first. I just want to make my life easier because once I start trying to find all the inverses, I'm going to be like, oh, well, okay, if I want to find 7 inverse, I'm going to do trial and error where I multiply 7 by all of the different options and figure out which one gives me 1 mod 30. So I was just kind of looking through the list and seeing if anything stood out to me as being potentially easier to do, because now when I, multiply 7 by everything in the list to see what the inverse of 7 is, I don't have to worry about 11. So just knowing it's 121 and knowing that's 1 mod 30, I was able to eliminate it, and kind of a little bit of luck of the draw, depending if you see these things or not right away. So those are maybe the easy ones. And then if I want to figure out 7 inverse, I really just have to go ahead and do like 7 times 7 is 49, and I'm not going to go ahead and figure out what that is mod 30 because I know it's not 1 mod 30. So then I'll keep going. 7 times 11, that's 77. And again, I know that's not 1 mod 30. So then, but 7 times 13 does give 91. And 91 is in fact congruent to 1 mod 30. So it took some trial and error, of course, but now I know that the inverse of 7 is 13. Then we also know that 13 inverse is 7. Another big advantage of figuring out my list of which elements can possibly have inverses before starting to compute inverses is that when I'm multiplying 7 by different things, I only have to multiply it by things from this list. I don't have to like say, oh, 7 is relatively prime, so now I'm going to figure out its inverse, and then I don't do 7 times 8, 7 times 9, 7 times 10. I just pick from the list of things that have inverses because that's the only place I'm going to get my inverses from. So now I have inverses for 1, 7, 11, and 13, and that means that when I look for 17's inverse, I'm going to just have to multiply 17 by itself, by 19, or by 23. You would just take 17, multiply it by itself, check what happens, mod 30. If that didn't work, multiply it by 19, check what happens. If that didn't work, multiply by 23, and you would get the inverse. So I'm going to write our conclusion here. We have that 17 inverse is 23, and we have that 23 inverse is 17. So the last number that we have left is 19. And we know that, we should have some intuition that inverses are unique. So like, since 17 is already an inverse with 23, it can't be an inverse with 19. So basically, like, the numbers are kind of partnering up for working on, I don't know, a quiz together or something, and 17's already partnered with 23, and 13 and 7 have partnered up, and 1 and 11 and 29 are all working alone. So 19 has to work alone too. So the only thing left for 19 to partner up with is 19. So 19 inverse, just by process of elimination, has to be 19. It's the only possibility for what 19 can partner up with from here. So then we have our complete list of what all of the inverses are, mod 30. So I just want to recap what we've done here. Whenever we're looking for the inverses mod n, those are going to be the numbers in the set from 0 through n minus 1, so that if we multiply those two numbers together, they give us 1 mod n. The only numbers mod n that can have inverses are the numbers that share no common factors other than 1 with n, so the numbers that are relatively prime. So in the case of something like Z5, 1, 2, 3, and 4 will all have inverses because these are all relatively prime to 5. And in the case of a non-prime number, we just go through the list of the numbers from 0 to n minus 1, and we just think through, okay, which ones are relatively prime, and we list those ones out. And of course, there are tips and tricks to make sure you have the correct number of these and maybe make computing this list a little bit faster, but it's a relatively straightforward process that you can just do even without knowing a ton of theory. And then in order to find the inverse of anything, you just take that number and you just try multiplying it by all of the other numbers in the list and just figure out which one, when you multiply, gives you 1 mod n. So here we did a complete list and found all of the inverses, but sometimes you might just want to know simply the inverse of 13 mod 30. So you'll just take 13 and you'll try multiplying it by all of the different numbers until you get one that gives you 1 mod 30. And as soon as you get an answer to that, you are able to stop because the inverses are unique. Each number only has one inverse. So when you're doing 13 and you multiply by 7 and you get 91, which is 1 mod 30, then you just stop. So the process itself can sometimes take longer depending how lucky you get, but the process does have a straightforward method of how you can determine the inverses of any number that is relatively prime to n.